Imagine downloading an entire 4K movie, literally, in the blink of an eye. That's not science fiction. That's the promise of Terahertz wireless, the next huge leap beyond 5G. But to get there, we have to solve a major engineering mystery, because the very tech we depend on today just completely and utterly breaks down. Let's dive in.
You know, the technology that powers pretty much everything. Our Wi-Fi, our 4G, our 5G, it's this brilliant thing called OFDM. For years, it has been the undisputed champion. But when we try to push it into the terahertz spectrum, which is the key to unlocking 6G, it doesn't just get a little weaker, it completely collapses. So what on earth is going on?
To figure out why our best tech fails so spectacularly, we've first got to understand the prize that engineers are chasing. And trust me, it's a big one.
The whole reason we're pushing into these ridiculously high frequencies is really simple: bandwidth. Think of the radio spectrum like a highway. Right now it's pretty crowded, but the terahertz band? That's like a brand new 10-lane superhighway with no one on it. We're talking about going from gigabits per second to terabits per second. This isn't just another upgrade, it's a total revolution in what's possible.
And our go-to tool for sending all that data has always been OFDM. I mean, think of it as the heavyweight champion of wireless. It's reliable, it's efficient, and it is the engine inside billions of our devices. It has always worked. Until now.
And these charts, wow, they show you the problem in plain sight. Just follow the red line. That's our champ, OFDM. Up top, at current 5G frequencies, look at it go. Performs beautifully. The error rate just drops and drops. But now look at the bottom three charts as we crank up the frequency into the terahertz range. The red line just hits a brick wall. It gets stuck in this OFDM failure zone, and it doesn't matter how much power you throw at it. It's just broken. The big question is, why?
Okay, so our investigation starts with OFDM's dirty little secret. It is a massive power hog, but probably not in the way you're thinking.
To get this, we have to talk about something called the peak to average power ratio, or PAPR for short. All it means is it measures how spiky a signal is. A low PAPR signal is nice and smooth, really power efficient, kind of like a flat road. But a high PAPR signal, like OFDM's, has these huge, sudden peaks. It's incredibly inefficient, like a road full of giant speed bumps for your power amplifier.
And this is where it gets kind of crazy. To handle those massive but occasional signal spikes without messing everything up, an OFDM transmitter has to dial its average power way back. It has to leave all this headroom, which means it's effectively wasting 90% of its potential power. That's like buying a brand new supercar and only ever being allowed to drive it in first gear.
This slide really connects the dots for us. So look at the chart on the left. That red line shows the absolute limit of a power amplifier. If a signal peak is too high, it smacks right into that ceiling and gets all distorted. To avoid that, spiky OFDM signals have to operate way down here. That's called the backoff. Now look at the chart on the right. That huge red bar, that's the massive power penalty OFDM pays because of this. At lower frequencies, fine, maybe you can afford to waste that power. But at terahertz, it becomes a fatal flaw.
Okay, so OFDM wastes a ton of power. That's really bad. But at terahertz frequencies, it gets hit with a second, even more devastating problem, a total double whammy of electronic noise.
And here are our two culprits, phase noise and thermal noise. You can think of phase noise as tiny, microscopic jitters in the transmitter's internal clock. And thermal noise is just what it sounds like, the random background static of the universe. Now here's the crucial part. Both of these get catastrophically worse under the exact conditions we need for terahertz communication. That's super high frequencies and super wide bandwidths.
And this chart, well, this shows the real killer. See, to generate a 1 terahertz signal, you start with a stable clock at a low frequency, and then you multiply it up and up and up. But every single time you multiply the frequency, you also multiply those tiny clock errors. It follows this nasty 20 log n rule, which means the noise doesn't just grow, it explodes. By the time we get all the way up to 1 terahertz, the phase noise is 40 decibels worse. That is a huge number, and it pushes OFDM deep into the zone where it just can't work.
And here's what all that noise actually does to the data. On the far left, you see a perfect, clean signal, 4 very distinct red crosses. That's what the receiver is hoping to see. But on the far right, well, that's what the signal actually looks like in a real terahertz environment. The noise has smeared those nice, distinct points into a messy, almost indecipherable blue cloud. How in the world is a receiver supposed to tell which point is which? The short answer is it can't.
So, we have our two culprits.
a massive power penalty, and a literal explosion of noise. Now it's time to see how they team up to deliver the final knockout blow to our champion. And here it is. This is the moment it all comes together. This chart shows you all the penalties stacked up. The red part, that's the power penalty from being so spiky. The purple is from that phase noise we talked about. The blue is from thermal noise. At lower frequencies, it's manageable. But just look what happens at 1 terahertz. They stack up to an absolutely insane 37 decibel penalty. To overcome that, you'd need more signal power than is physically possible. This right here, this is the smoking gun. Case closed.
So, if our champion, OFDM, is down for the count, who's left standing? Who can actually take its place? Well, the survivors are the schemes that don't have those fatal flaws. A simple, tough-as-nails workhorse called QPSK, and a really clever hybrid called DFT-s-OFDM. Let's see why they're the ones that win.
And this table just makes it crystal clear. Look at that PAPR column. For both QPSK and DFT-s-OFDM, it's 0. 0. No power penalty. Now look over at phase noise sensitivity. Both are low, while our old friend OFDM is very high. They are basically immune to the two biggest problems that absolutely kill OFDM in the terahertz world.
So how does all this get turned into real-world advice for the engineers building this stuff? Well, this heat map is basically the cheat sheet. In the green zones, down below 50 gigahertz or so, OFDM is still a great choice. But as you move to the right into the higher sub-THZ and THZ frequencies, the map just turns red for OFDM. The path forward is obvious. Engineers have to use these tougher, more robust schemes to build our 6G future.
So, the case is closed. We know exactly why our wireless champion fails at terahertz speeds, and more importantly, we know who its successors are. And this isn't just some academic puzzle. This is the fundamental knowledge that engineers are using right now to design the 6G and even 7G networks that are going to shape our world. The next time you hear about terabit wireless, you'll know the incredible engineering mystery that had to be solved to even make it possible.